Yeah, welcome to this fourth lecture. So today we'll finish off a bit of chapter 2 as quickly as possible. So last time we talked about matrices that were self-adjoint and that were positive. So in the sense that P, if I take a matrix and take the inner product here, I get something larger than 0 whenever my vector is in k to the power n. K is bold K is R or C, and P is a real or complex matrix with real or complex coefficients. And what we talked about last time was that we can consider kind of these positive self-adjoint matrices is kind of lying inside all of the matrices, or at least all of the invertible matrices, in a similar way to the real numbers inside of the complex numbers, in that they have well-defined logarithm and square root. And the idea was that, and the way you did this was that we showed that self-adjoint matrices that are positive, you can then just change, do an orthonormal change of basis, and that will make the matrix look like a diagonal matrix with real coefficients that are all strictly positive. And then you just do the square root or the logarithm with of all of these numbers on the diagonal. So what we didn't do last time was the following theorem, which is the polar decomposition, which was what we were aiming for. So if we have any invertible matrix, so yeah, we can do it in C, since real matrix will then be a special case. So any of these kinds of matrix can be written uniquely as U, so A equal to U times P, which is U times E to the power X, where U is, I'll have to do curly U, the unitary matrix. It's a unitary matrix, and P is positive and self-adjoint. And X is just self-adjoint. And X is here then just the logarithm of P. So this, like these two things are equal because you can uniquely represent P as the exponential of a matrix that is simply just self-adjoint. So this is then becomes the polar decomposition. So let's do the proof of this. So as I mentioned last time, this decomposition sort of reminds you of how you can decompose a complex number into a positive real number times a unitary element, unitary complex number, so some rotation in the complex number, and this is sort of the equivalent, but in higher dimensions. So we do several steps. So step one. So we start off with define, let's say Q, which is a star A. So this will, let's say, so Q is will then be self-adjoint. Because if I take A star A and do the adjoint, then I have to reverse the order. So I have to do A star and A star. A for the star for the conjugate transposed, and this is again A star A. And it's positive. Because remember that the conjugate transposed is the one, it's the analog of the transpose for real matrices, is the one that if you take V A star A, this is the same as doing, then I can move this to the other side and take the dual, and so I get here A V, which is now V square, and this vector is not zero, since V is not zero, and A is an invertible matrix, right? So invertible matrices have trivial kernels, so that means that anything that's non-zero will also be non-zero after the image. So this, so hence it will be positive, right? So here I can, so taking an arbitrary matrix, I can construct a positive self-adjoint matrix in this way. Now since this is positive and self-adjoint, it has a square root. So I can define P to be a square root of A. And then step 3 is, which will then also be positive and self-adjoint. And then finally, I define A equal U P. That is, U is equal to A P inverse. So and then since P inverse is also self-adjoint. So you can, so yeah, let me just show that. So if I take P and P inverse and take the dual, that should still be the identity, since the identity is self-adjoint, but it's also P star P inverse star. But this is then P inverse star. So hence P inverse star has to be equal to P inverse, because if I multiply with P, I get back to the identity. So just because of this changing of order, it follows that P inverse is also self-adjoint, and then we can look at what happens if I take U star U. Then that's equal to A P inverse star A P and then A P inverse. So here again, the conjugate transpose changes the order. So I get P star inverse star, which is just P star inverse, and then A star A P inverse. But A star A, this was just P square. So this is P inverse times P square times P inverse, which is the identity. So that means that U has to be a unitary matrix. So this completes the proof for existence. So proof of uniqueness. If A is equal to U tilde P tilde, U tilde is unitary, P tilde is self-adjoint, positive, then we can write P tilde as P tilde as AU as U inverse, U tilde inverse A, but this is just U tilde star A. But since P tilde is self-adjoint, this should also be U tilde. This should also be the adjoint of this product here, which is A star U tilde. So since this matrix is switched around, I should be able to write it in this way here. So then, and that means that if I take the square, then this should then be equal to this version here of P. So A star U tilde, and then you have U tilde star A. Now these are unitary, so this just becomes the identity. So here you have A star of A. So the problem, so we see that P square needs to be equal to A star A. Now, by uniqueness of square root for positive self-adjoint matrices, we have that P tilde has to be equal to P, which it was the square root of A star A. So and then it follows that U tilde, which is then A of P star inverse, is equal to U. So because positive matrices, positive self-adjoint matrices have a unique square root inside of the positive self-adjoint matrices, they have to be equal. And this shows then the uniqueness of the decomposition. So, and this then completes the proof because we show that this kind of decomposition exists. And we shown that it is unique. Now note that it's not in general true that like if you have a matrix here and then square that's equal to this, then there is a unique square root of this. That's not what I'm saying. So just like for a real number, for example, 4, you have 2 square roots, so 2 and minus 2, but there's a unique one that's positive. It's the same way here, that if you have a positive self-adjoint matrix, there is a unique one that's also a square root that's also positive and self-adjoint. Okay. Sorting. So let's see, there are some other results here. So, but I think I'll skip those because they're not so difficult to understand. Read 224 corollary 4 in notes yourself. And then I'll continue with the main topic of today, which is Lie algebras. Now, as I mentioned before, that we don't do the general definition of a matrix Lie group because we want to avoid dealing with manifolds. So we'll briefly mention it here and there, but we'll not delve deeply into it. On the other hand, when it comes to, and then we restrict ourselves to matrix Lie group when we're working with this, but on the other hand, when it comes to Lie algebras, we have no such restrictions. So because it's just an algebra, it's a particular operator on the vector space, so we can deal with this in the following way. We can deal with a general definition. So what is the definition of a Lie algebra? So
Alan, two seconds. I think the reference corollary 224 should be 219.
Should it be 219?
I think so, yeah. At least in my book here.
So
I think he's referring to his lecture notes.
yeah.
Oh, it's your lecture notes. Sorry, in notes.
Yeah,
but
sorry, we can do.
Yeah, sorry. Yeah, sorry. Yeah.
What was it in the book?
Yeah, it's 219 in the book. Yeah.
Is that the one where they do SL and all of the others?
Yes. Yeah.
Yeah.
Sorry, I just didn't read carefully.
No, but that's fine. So it's good, nice to have both. Okay, so what is a Lie algebra? So finite dimensional real or complex the algebra is a real complex vector space which we usually denote by this German factor G. So math, this is a slash math, my attempt at a slash math frac G in terms of the LaTeX code. And so it's a either real or complex vector space with bilinear operation which we denote by these sorts of brackets here that go from G cross G into G. So it goes from X, Y to bracket X, Y. And so we're saying that it's bilinear, so it should be linear in all components with properties. Yeah. So as I said, bilinearity so if you have an element, a constant c in your either real or so where k is r or c, then multiplying with an element of this bracket is the same as multiplying with the scalar in x is the same as multiplying with a scalar in y. So that's the first condition, which is not so mysterious. The second is skew symmetry. Which is that x y should be equal to minus yx. And finally, it's the more mysterious thing called the Jacobi identity. And how does that work? Well, it works as following. If we take x, if we take 3 elements, so we first take the bracket of y and z, and then we take the bracket of x with x. Then if we cycle the elements here, so we can cycle it towards the left or the right. Let's cycle them to the right. So if we do a complete cycle of this bracket like this, involving 3 elements, then we get 0. So these two first are quite straightforward. The last one is a bit more difficult to understand why it appears. So I'll explain you a little bit more about this when we do the example. So it won't be the first example, but it will be the second example. I'll explain why we have this Jacobi identity. So let's do examples. So the first example that you've seen is R3 with a cross product. So if we define bracket UV as the vectors U and V crossed, this will be a Lie algebra. Remark. Notice that this algebra is not associative. So if we take E1 to be 1, 0, 0, E2 to be 0, 1, 0, and E3 to be 0, 0, 1, then if I take E1 cross E1 cross E2, that is E1 cross E3, which is minus E2. Whereas if I take E1 cross E1 cross E2, I get 0. So in general, Lie algebras are not associative. So unless the Lie bracket does nothing, this will be the case that it's not associative. Next example, if we take M and K, so all K n by all n times n matrices, we can define the bracket of x and y as x y minus y x. So let's call this 1, or we can say, so this bracket is called the commutator bracket. So this will be Lie algebra which we denote by the very suggesting name of a small g, l, and k. So g, l, and k are all n times n matrices with this commutator bracket. And we'll see later how that relates to the other GL with large letters. So, and then C is that the same approach works for any, or we can say works if we replace the either real or complex matrices with any associative algebra. So if we have some sort of other associative algebra with some sort of multiplication, then we can do the same commutator bracket and get a Lie algebra. And that's exercise 3.1. So, and then the fact that you have associativity will give you this Jacobi identity. And so why do I bring this up because the reason I'm bringing this up is that it seems very strange to have this extra identity. Why do I have this extra triple identity down here for the definition of the algebras? Well, it is because if you do this sort of commutator bracket from something that is associative, this is what you get for free. So Lie algebras are not associative algebras, but this Jacobi identity plays a similar role to this, the usual identity that we have with associativity. I'll pause again, recording again. Then I'll do one more definition. So I'll say that no, I'll do one more example and then we do a little break because I want to give you an exercise at the end of the example. So example D. So if X and Y are in this G, L, N, K, so that was all of the matrices, then if then the trace bracket X, Y, that's the trace of X, Y minus the trace of Y, X, but the trace, you can switch the order. So the trace is always 0. So whenever I take the bracket, I always get a matrix with trace 0. Hence, if we define S, L, and K, which are all X in GL and K, with trace equal to 0, and brackets equal to the commutator brackets, then it is a Lie algebra. So because if I take just the trace-free matrices, then the bracket will always be also inside the trace-free matrices. And so this will be then also a Lie algebra as well, right? Now, the exercise before the break, write G, L, and K as S, L, and K plus some other and some other space where both of these are subalgebras. So we haven't done the formal definition of a subalgebra, but okay, it's one where if you restrict the bracket, you get you still get a Lie algebra. So you can think about this a little bit, and then we take a break until 1/4 past. Yeah, so here we have this welcome to the second part. So we can, of course, then decompose all of our matrices into the trace-free matrices, and then the subalgebra spanned by just the identity matrix. And we note that the identity matrix commuted with any element is 0. So this one is, and of course the identity matrix with itself is 0. So this will be a subalgebra, and brackets here will not go into brackets here, and the other way around. So that means that we can write x as y plus some, let's write the actual formula, trace over x divided out by the dimension equal to the identity, where y is in S, L, and K. And then if we take the bracket of 2 elements, x1, x2, this just becomes, so this is then y1 plus the trace of x1 divided by n, identity, y2 plus trace of x2 divided by n, identity. This will then just be the brackets of these trace-free parts. So the Lie algebra of all matrices can be decomposed into trace-free matrices, and then this additional part spanned by the identity, which contains all the trace. And since the identity commutes with everything, the bracket is only determined on the side where you have trace at the trace-free part. So this is an example of a direct sum of Lie algebras. And a direct sum of Lie algebras is the case where we take the vector space, so G plus H, and brackets x 1, y1, x2, y2, and then the brackets is just that you take the brackets here in G for the first part, so x1 and x2 are in G, and y1, y2 are in H. And then you take the bracket in H for the second part. So the previous decomposition we saw, that's a special case of this, with the only difference is that this H had all brackets been equal to 0. So one thing to note, to be careful about this, is that we use this symbol, direct sum, for both direct sum of vector spaces, but sometimes for also this direct sum of the algebras that is meant in this thing here. But most of the time, we just mean that they are written like this for vector spaces. So don't assume that if you see something like this, that the brackets are given as this, unless it's mentioned explicitly. Let's see, this. So a couple of more definitions, and then we look at special types of Lie algebras. So a Lie algebra given with a vector space and a bracket is called abelian, or commutative, if the brackets of x and y are equal to 0. So our algebra spanned by just x, that's and then just the identity, that's an example of a commutative algebra, commutative Lie algebra. And we'll talk a little bit later, but one thing you'll see is that there's a lot of concept names that we use for groups that we're going to introduce for these Lie algebras. And what you're eventually going to see is that they're going to correspond. So these abelian Lie algebras are going to correspond to abelian Lie groups and so forth. Are there any questions before I continue? Okay, then we'll look at some special cases of Lie algebras, and this is often related to the concept of an ideal. So types of Lie algebras. So so first definition, let's see, so H inside of G, which is a Lie algebra, is an ideal if x, y is in H, whenever x is in H and y is in G. So this is not the same as a subalgebra, which means that x, y is in H whenever x and y are in H. So an ideal is something that's stricter than having a than having a subalgebra. So ideals are subalgebras, but subalgebras are in general not ideals. So and the major difference here is that Y can be whatever it wants from the general Lie algebra. So let's do some examples. So in let's say G, L, and K, both S, L, and K, and the span of the identity are ideals. So if I take the identity, then bracket with the identity always gives me 0, and 0 is in the span of identity. So this will always be an ideal. And then this, we saw also that if you had something that was trace, any matrix, then the Lie bracket is always trace free. So trace free matrices are also ideals. So next, for the same reason that 0 is in any subspace, the center that's this mathfrak set. How do I do that? Something like this. Something like this. So it's supposed to be, I'm just going to write it like this. Something like this. So set of G, which is the set of all elements in G, such that X, Y is equal to 0. For all Y in G. So that's called the center. And this is an ideal. Because, okay, all the brackets, by definition, all brackets here will become 0, which is in the subspace. So the center is an ideal. We can do the Lie algebra, which has the suggestive name E n, so a factor E, small e, which consists of all matrices like this, 0, 0, or now we're doing en. Let's not do that. Let me not do that. So because then I have to introduce the orthogonal matrices, or the skew symmetric matrices. Sorry, let's not do that. So let's just do general Lie algebra. Okay, we can call it sometimes called the F. So let's call it F n, which is the group of matrices A, 0, 0, where A is in, just a general matrix. Let's make it real. And A is in Rn. So these belong to n plus 1 real matrices. Now, what happens if I take a Lie bracket of matrices of this type? So it's general matrix, but I have just zeros on the bottom. So if I take a Lie bracket of A, 0, 0, small a with B, 0, 0, B, what I get is that I get a matrix that is a B. Here I just get zeros. And here I get B minus BA. So this you can verify yourself through matrix multiplication. So in particular, this is Lie algebra. We see that it's closed under the commutative bracket, so it's Lie algebra. Define H inside of f n and P inside of f n as so that H is the collection of matrices which are H 0, 0, has just zeros for A, and P is the other type of matrices. Then if I take the bracket of H elements in H with elements in H, I go inside H. If I take brackets of elements of P with itself, I get 0. And if I take H with P, I go inside of P. You see that from the definition of the bracket? So in here, so this notation just means I'm taking all elements from here, right? So hence, both H and P are ideals, now are subalgebras. Only P is an ideal. So we can write this as G bracket with P go inside of P. Or yeah, we define this affine as the full G, then yeah, I should write it as F n P. This is goes inside of P. So that's the way you can define an ideal is through this formula here. So in this case, we see that only P is an ideal because only for P will brackets end up in P no matter what other elements. So it doesn't mean that all brackets end up here, but if at least one of them is in P, then they will end up in P. Are there any questions to this? So ideal seems probably a bit weird. It depends a bit how much Lie algebra how much general algebra you've had, if you've seen ideals before. In general, what we'll see is that ideals will correspond to normal subgroups. So that's why they will be interesting. And also it allows you to define, you can take quotients and still end up with Lie algebras if you have an ideal. So we have the following definition related to an ideal. We call Lie algebra simple if the only ideals in, so a Lie algebra, let's say G, simple if the only ideals in G is 0, so the 0 ideal just consisting of 0, 0 is always an ideal, and G itself. So 0 will always be an ideal, the full group will be always an ideal, and then we call it simple if that is the only ideal that we have. So let's write this a bit better. And the reason we're interested in simple Lie groups or simple Lie algebras is that basically these can be thought of as some of the base components. You can't really break down a simple Lie algebra and study it in any simpler components, let's say, whereas if you have some ideal, you can take a quotient and stuff like this. I should probably write some of this down. I can write it at the end. I'll do an example first, and then I'll write this about the quotient afterwards. So let's define S. So let's define SL to should we do C or 1? Let's define SL to R. Sorry, to R. So what is SL? SL was then all trace-free 0. So that's all types of matrices on the form A, B, C minus A in 2x2 matrices. So A, B, and C are real. So this has, so let H be an ideal. An ideal non-zero. We have a basis for SL to R given by x equal to 1/2, 0, minus 1, 1, 0, y equal to 1/2, 0, 1, 1, 0, and then finally set equal to 1/2, 1, 0, minus 1, 0. And these have brackets x, y is equal to set x is equal to y, and y set is equal to minus x. So if we see here that SL2C, that's determined by 3 real numbers, so we can find a basis of 3 matrices. We choose these particular matrices because they have nice explicit vector brackets that are given on the following form. So very often, at least with these low dimensional Lie algebras, very often you can find a basis, and then all you need to do, all the information you really need is stored in whatever brackets are given for these particular matrices. So and you can check this yourself by completing the commuter brackets for these 3 matrices. So assume that okay, let's call, yeah, okay, fine, U. Let's call it W, so to not confuse with unitary matrix. U is AX plus BY plus CY, which is in H, A, B, C, not all 0.
C said, right?
Yes, C set, yeah, like this. So we have, so if I have if H is non-zero, then there exists some element W which is not 0 inside of H, right? But then I can do the following trick. So I just look at what happens if I apply each of these vector fields twice. So for X, I get BY plus the set. For if I do Y twice, I get AX plus CY. And if I do set twice, I get AX plus BY. See, And here's so C set. Sorry. So there's a mistake in the notes that I have to fix. So so doing this double bracket, we can sort of get rid of one of these things, either the part with X, the part with Y, or the part with Z. All have to be in H, right? Because since it is an ideal. So since I took an element of H and I took brackets with it, also the resulting elements have to be in H, and since it's since this is a subspace, I can subtract each of these elements from W, and so I get that AX, BY, and C set has to be in H as well. So let's say, for example, so one of these has to be non-zero. So we can, for example, say, what if A is non-zero? And then it's the same proof with B non-zero and C non-zero. If A is non-zero, to 0, that means that X has to be in H. But this implies that Y, which is X set, right? Or yeah, no, set X. Is in H. And it also implies that set, which was XY, is in H. So hence H has to be the entire the algebra. So conclusion, our Lie algebra SL2R is simple because if I take an ideal and I assume that it's non-zero, then immediately I get that it has to be the entire Lie algebra. Now, I'll do a remark, which I mentioned before. So if H is an ideal in G, then we can define Lie algebra T quotient out by H, which is the quotient vector space with brackets that the brackets of an element x, so x, y, and g. What are the elements in the quotient? Well, these are elements that differ by the equivalence class, differ by an element in H. So I can write them at x plus H and then y plus H. And the bracket is simply defined as being just x, y plus the elements in H. And in general, if you just have a subalgebra, some subspace, then this formula that makes no sense because it would depend on what kind of elements you pick in H here and here. But since the brackets with these elements anyway end up in H, because it's an ideal, then this thing makes sense. So here again, the analog of normal subgroups. Normal subgroups, we can define quotients and we still have a group. Ideals, you can define quotient and you still have Lie algebra. Like if you took a quotient of just a subalgebra, you can get the vector space, but you don't get any. But there's no way of defining a proper brackets on this subspace. And so this is why we are interested in sort of simple Lie algebras, because they are algebras where we cannot define these smaller quotients by quotienting out by any subideals, because there are no subideals. They are just 0 and the full space. So the next topic is are nilpotent and solvable on the algebras. Since I'm running out of time here, I'll do more types of algebras next week. Of the algebras next week. So I'll spend the 4 last minutes talking about derivations, because I sort of skipped over that. And since we have a little bit of time, I just want to talk about what a derivation is. So definition, a derivation from a Lie algebra to itself is a linear map with the property that dxy is equal to the bracket of d of x y plus the bracket of x and d and y. So in this sense, why is it called a derivation? Well, it's because it satisfies this kind of Jacobi identity, right? If you want to differentiate the whole, then you added sort of the d of each part. So that's why it's called a derivative. And the last results we'll end on is the following theorem. So if set is in G. Define small add set from G to G as add set of X equal to the bracket of X and Z. Then add set is a derivation. So this is called an inner derivation. So yeah, let me put this as A. So, and B is that if I take consider this as a mapping in itself and define add the bracket of add X and add Y. So that is the mapping add X, add Y minus add Y, add X. Then this is equal to add of the bracket X, Y. So these add maps, they are always derivations. And if you take the commutator bracket of them, you get the same results. So yeah, and the proof is just the Jacobian entity. So both A and B are just restating of the Jacobian entity. So this is one way we can take advantage of the Jacobian entity is we get the following result. And because of this, you can sort of see this add map as being kind of a Lie algebra homomorphism, which you didn't really talk about, from G to the derivatives. And yeah. And that's the end of the lecture.